Welcome back to The Explainer. So in part one of our networking series, we covered the foundational concepts of LANs, MANs, and WANs. We established what a computer network actually is. But today's Explainer, we're focusing heavily on the physical infrastructure. We're going to look at exactly how we lay the roads and build the intersections to connect these digital cities together. Now, here's the million-dollar question when you're setting up a network. How do you actually arrange the cables and signals to prevent digital traffic from completely crashing? I mean, do you string everything together in a single straight line? Do you build a loop? The way you lay out this grid is absolutely vital to the health and efficiency of your entire system. Here is our blueprint for today. We'll define what a network topology actually is, explore the 4 major physical layouts, look at the essential hardware directing your traffic, and finish up with a showdown between legacy hubs and modern switches. Section 1. What is network topology? Let's start with the big picture. Basically, topology is just the architectural layout of your system. It defines how devices are connected to each other and exactly how data flows between them. And this isn't just about making things look tidy in a server room. Choosing the right topology literally dictates your network's speed, its reliability, its overall cost, and how easily you can scale it up later. Keep in mind, this encompasses both the physical topology, like where the actual cables run, and the logical topology, which is the invisible path the data actually takes.
Or major topologies.
Moving on.
We're looking at bus, star, ring, and mesh. Let's explore how we can build these digital roads.
First up is the bus topology. Picture this. Every single device shares one main central highway, which we call the backbone. Data travels straight down this backbone, and while every device technically receives the data as it passes by, only the intended recipient actually accepts it. This is exactly how early Ethernet setups were designed back in the day.
Now, when we weigh the pros and cons, the bus topology is incredibly simple and cheap to install, mostly because it requires very little cabling. But there's a huge fatal flaw here. If that single main backbone cable breaks, your entire network goes dark immediately. Plus, as you probably guessed, the more computers you add to that single line, the worse the traffic jams get, and performance just tanks. Because it's so fragile and hard to troubleshoot, you'll rarely see it used today.
So let's move to a much more common design, the star topology. Instead of a single shared line, every single device gets its own dedicated private cable connecting it to a central controller, usually a hub or a switch. All data travels from the computer into the center and then out to its destination. This is exactly how your modern home Wi-Fi router operates right now.
What's really brilliant about the star layout is how it isolates problems. If someone accidentally cuts one cable, only that specific device drops offline. The rest of the network doesn't even notice. It's super easy to troubleshoot and expand. The trade-off? Well, you're going to need a lot more cable, and you have to buy that central piece of hardware. Plus, if that central switch dies, the whole network goes down. But honestly, despite that single point of failure at the center, the fault isolation makes this the absolute dominant choice for home and office networks today.
Next on our list is the ring topology. Just like it sounds, each device connects to exactly 2 neighbors, forming a closed circular loop. Data travels systematically in one single direction around the ring, passing through each device until it reaches its target. You'd see this in legacy token ring networks, or sometimes in modern high-speed fiber optic networks that use a dual ring setup for backup. The major advantage here, incredible traffic control. Because data only flows one way, there are absolutely no collisions, giving you incredibly consistent performance even when the network is getting hammered with heavy traffic. But much like a single-lane roundabout, if one single device breaks down, the entire loop is severed and everything halts. Adding a new computer also means temporarily breaking the ring, which disrupts the whole network. And finally, we reach the mesh topology. This one is like a massive, complex web of intersecting lines, because every device connects directly to multiple, or literally all other devices in the network. This creates a vast array of redundant paths. If one road is blocked, the data simply takes another route. You'll usually see mesh networks in 2 distinct flavors. A full mesh means absolutely everything is connected to everything else. It offers maximum reliability, which is exactly why the military and critical power grids use it, but the sheer amount of cabling makes it overwhelmingly expensive. On the other hand, a partial mesh connects devices mostly to the nodes they talk to most often. This balances that incredible reliability with a much more practical cost. Fun fact, the internet itself is the ultimate sprawling example of a partial mesh topology. Section 3, Essential Network Hardware Devices. Okay, so we've laid out our digital roads with our topologies. Now let's zoom in on the actual hardware boxes with the blinking lights, the traffic controllers of your network. First up is the hub. Now, a hub sits at the center of a star topology, but honestly, it's not very smart. When a hub receives a packet of data, it acts like a guy with a loudspeaker in a crowded room. It blindly shouts and broadcasts that data out to every single device on the network, even if the data was only meant for one specific computer. As you can imagine, this creates massive, unnecessary congestion and totally tanks your network's efficiency.
To fix all that congestion, the industry evolved to the switch. A switch might look exactly like a hub on the outside, but it acts as a highly intelligent intersection. When a switch receives data, it actually reads the hardware's MAC address to identify exactly which device the data is meant for. It then opens a private, dedicated lane to forward that data only to the intended recipient. No shouting, no broadcasting, zero unnecessary traffic. Now, while switches are busy connecting devices to each other inside your house or office, the router is what connects your entire local network to the outside world. Routers literally route data between different networks. They do this by reading IP addresses, allowing your private local network to communicate securely with your internet service provider's massive network. But to actually speak to that internet service provider over the infrastructure spanning your city, you absolutely need a modem. Think about it. Your computer speaks in digital data, right? Just ones and zeros. But the older telephone or cable lines running down your street, they carry analog signals. The modem modulates and demodulates these signals, acting as a vital translator so your digital network can physically travel across those outside wires. And finally, to get those digital signals out of the cables and into the air for your smartphone or your laptop, you use an access point. This device essentially bridges the gap between your physical, wired Ethernet network and your wireless Wi-Fi devices. A quick note here, while your home router usually has an access point built right into it, they are technically two completely different functions. Section 4, Hubs versus Intelligent Switches. Let's bring this all together with a quick showdown to illustrate exactly why local network hardware had to evolve. When we compare them side by side, it's pretty obvious why the switch is the absolute backbone of modern networks. Hubs are cheaper, for sure, but their blind broadcasting creates totally unmanageable traffic jams as networks grow. The intelligent routing of a switch completely solves these speed and collision issues. The massive efficiency you gain by only sending data to its intended destination easily justifies the slightly higher price tag, completely rendering hubs a thing of the past in modern tech design. So, we now know that star topologies and smart switches have built the physical infrastructure of our digital cities, but that leaves a massive, lingering question for us. How does the actual data cargo move across these roads? What exactly is a data packet, and what on earth is the OSI model? I mean, really think about it. How does an image on a server thousands of miles away perfectly rebuild itself on your screen in a matter of milliseconds? It's like magic, but it's pure engineering. We are going to uncover that fascinating mystery in part 3. See you then!